trying to solve what is sine inverse of sine of 7 pi over 6. And first of all, could you do sine of 7 pi over 6 from your pi plate? What is it equal to?
1/2.
1/2, close. It's in quadrant 3, so then what would I have to put here? Negative 1/2. Okay? And then we do sine inverse of negative 1/2. So one of the things that I find really helpful when doing questions with sine and with sine inverse, okay? Sine gives you an angle and it finds you the ratio, the opposite over hypotenuse. Sine inverse gives you the ratio and decides you should try to find the angle. So what angle gives you negative 1/2? Well, there's a bunch of them. Right? There's answers in quadrant 3 and quadrant 4 where sine is negative. You could do 7 pi over 6 and 11 pi over 6. But sine inverse is a function, which means it can only give one answer when you type it into your calculator. And if you type in sine inverse of negative 1/2 into your calculator, it would give you negative pi over 6. Now, how do we figure this out? And how do we know that this is the answer? Okay? And it's all based on the graphs that we did yesterday. Here's the graph of sine when it passes the horizontal line test. And one of the things that I find is really helpful when looking at this is you can see that when sine passes the horizontal line test, from 0 to pi over 2, can you see that these are positive answers in quadrant 1? And here, 0 to negative pi over 2 is actually negative values in quadrant 4. Because 0...
Please excuse the interruption. Can we please have all grade 10s to the theater? All grade 10s to the theater. Thank you.
Here's 0 to pi over 2. Here is 0 to negative pi over 2 on your pi plate. 0 to pi over 2 is positive answers in quadrant 4. But 0 to negative pi over 2 would be negative angles in quadrant 4. And so when you do your sine inverse function, the answers are always going to be angles that are positive in quadrant 1 or negative in quadrant 4. Because your answers go, your y values go from 0 to pi over 2. Those are positive angles in quadrant 1. And 0 to negative pi over 2, which are negative answers in quadrant 4. So what I find helpful, boy, that's really slow today on responding to stuff. Okay? Sine inverse of x. There we go. So, first of all, just an idea. When you're doing a sine inverse, you're solving for an angle. When you're doing sine of something, you're solving for a ratio. So sine inverse, you've done that before. That solves for an angle. Okay? Sine inverse of a positive number will be a positive angle always in quadrant 1. And sine inverse of a negative answer, if you have a negative ratio, will always give you a negative angle in quadrant 4. So now I'm going to re-look at this for you guys and see how this can help us solve this question faster. Okay? I want to find sine inverse in the end. I'm going to be finding sine inverse of something. And so I'm looking for an angle. Normally when you have an inverse and a function, they cancel each other out. Normally when you square something that's square rooted, those go away. But it doesn't happen in this case because of restrictions on your domain. So when I'm finding sine inverse of sine of 7 pi over 6, I know it's going to be the pi over 6 family. Because they're going to cancel out. It still have to be part of the pi over 6 family. But it's not going to be 7 pi over 6 because sine inverse only has answers in quadrant 1 or quadrant 4. If the answers are in quadrant 1, they're positive angles. If the answers are in quadrant 4, they're negative angles. Now, since sine of 7 pi over 6 is negative a half, I would know I'm looking for a negative angle in quadrant 4. And the pi over 6 family that belongs in quadrant 4, that's negative, would be negative pi over 6. We're going to make one of these helpful hints for sine inverse, cos inverse, and tan inverse. And they can help you solve things really quickly. Like, for example, if I had sine inverse of sine of, let's say, 7 pi over 3. 7 pi over 3 is in which quadrant? Quadrant 1. Is sine positive in quadrant 1? Yes, so this will be a positive answer. So if I'm doing sine inverse of something positive, I'm looking for a positive angle in quadrant 1. The answer to this will be pi over 3. All right. Even sine inverse of sine of 2 pi over 3. Do you see that this is in quadrant 2? Sine is positive in quadrant 2. So I know this is going to be positive. And so what is my pi over 3 in quadrant 1? The answer to this is pi over 3. Yes?
Is the answer always either going to be pi over 3, pi over 4, pi over 6, or negative pi over 3?
It depends whatever your angle is to begin with. Like, I could give you this, sine inverse 8 pi over 7 in there. What's your reference angle? Your reference angle for this would be pi over 7. What quadrant is 8 pi over 7 in? Quadrant 3. Is sine positive or negative in quadrant 3? Negative. So I know that this answer is going to be negative, but it's not on my pi plate. I can't even figure it out. But when I sine inverse it again, now I want to solve back for the angle. And the answer to this is, which is your pi over 7 family in quadrant 4 that's negative? The answer would be negative pi over 7. So sine inverse solves for angles. It'll always find an angle either in quadrant 1 or in quadrant 4. But the angle in quadrant 4 is negative. And we can, again, we see that from our graph. Right? When you do sine inverse, you're solving for y values. Notice your y values range go up to pi over 2. That's positive answers in quadrant 1. They go down to negative pi over 2. And 0 to negative pi over 2 are negative answers in quadrant 4. Okay, with that, let us go to our next graph. Here is our cos graph. Cos graph starts at a maximum, and I can go all the way to here before, like if I kept going here, do you see that it wouldn't pass the horizontal line test anymore? And I can't go backwards at all with this, because then it wouldn't pass the horizontal line test there. So again, the rule for drawing, start at 0 for x. Go in the positive direction first and draw as much as you can before you don't pass the horizontal line test. Then you go in the negative direction. And this one we can't go in the negative direction at all. So I want you to notice though, cos is different. Cos gives you quadrant 1 and quadrant 2 places. So when I do the inverse and I switch everything around, wait for it, maybe. There we go. My answers are positive in quadrant 1 and positive in quadrant 2. And this was really confusing in grade 11 and grade 12, so we didn't even let you ever type in cos inverse, sine inverse, or tan inverse of negatives ever. Do you remember? We said when you find a reference angle, you have to do sine inverse and just make it positive so you don't screw things up. And it was especially cos that screwed things up. Because if you did cos inverse of, here I'll even show you. You were in radians. Let's just go to our calculator and relive some grade 11 and grade 12. So you were finding your reference angle. And if you did sine inverse and you put in 0.5, you're like, okay, that's my reference angle. And if you did sine inverse and you accidentally put in negative 0.5, you were like, oh, it didn't matter, just ignore the negative. But with cos, you really got screwed up if you did the negative. Watch this. Cos inverse of 0.3, this is your actual reference angle, 1.266. If you accidentally did cos inverse of negative 0.3, you still got a positive answer. And you were tempted to think this was your reference angle. But 1.87 is actually in quadrant 2. Sine inverse gives positive ones in quadrant 1, negative ones as negative angles in quadrant 4. Cos inverse gives positive ones in quadrant 1 and negative ones as positive angles in quadrant 2. And lots of times students did this and used 1.87 for their reference angle, which is wrong. The reference angle is 1.266. So in grades 11 and 12 we said, when you're finding a reference angle, only do the positive value. And the reason for this is because the negative answers can sometimes throw you off, especially with cos. Because for cos to pass the horizontal line test, it can use positive answers in quadrant 1 and positive answers in quadrant 2. So if we will make that shortcut again, right? Cos inverse of x solves for angles. If you have cos inverse of a positive value, your answer will be a positive answer in quadrant 1. If you have cos inverse of a negative value, it'll put out an answer, a positive answer, in quadrant 2. So if I asked you cos inverse of cos of 4 pi over 3, you know your answer is going to be part of your pi over 3 family because that's your reference angle. Is cos of 4 pi over 3 positive or negative? It's in quadrant 3. Cos is negative in quadrant 3. So cos inverse of a negative value will always put out a positive angle in quadrant 2. If your reference angle is pi over 3, what family member do you have in quadrant 2? The answer to this is 2 pi over 3. Because, first of all, cos of 4 pi over 3 will come out as negative 1/2. If I draw that on my graph, negative 1/2 is right here. But if I do cos inverse of negative a half, it'll go up to that point right there at 2 pi over 3. Okay? So it's kind of neat to see it on the graph what's happening. Okay? But you are very tempted, right? The number one mistake in this question is students write 4 pi over 3 because they just go, oh, cos and cos inverse, they cancel each other out. Sort of cancel each other out. Yes, you get an angle again, but the angle has to be within the domain and range of the functions you're working with. And in order for these to be functions, we had to restrict the domain of cos, which then restricts the range of cos inverse. So here's our properties. Domain goes from -1 to 1, range from 0 to pi. We got a y-intercept and an x-intercept. It's neither even nor odd because you can't reflect it over to match up either way. You can only do cos of cos inverse of x if x is between -1 and 1. And you can only do cos inverse of cos of x if x is between 0 and, I mean, it's only equal to x only if it's in quadrant 1 and 2 to begin with. Otherwise, we have to think about the positive and negative shortcut thing that I showed you. Okay. Tan inverse. If you start drawing tan, and you go to the right, you hit an asymptote, and you can't jump over that asymptote. So then you go to the left, and you only draw tan from -pi over 2 to pi over 2. So what do we get? We get here from 0 to pi over 2 is positive answers in quadrant 1, and we have negative answers in quadrant 4, just like before. When you go to graph your inverse, you switch your x and y values, your vertical asymptotes become horizontal asymptotes. And if I write the same shortcuts as before, right, we know that tan inverse of x solves for an angle. And so if we have tan inverse of a positive value, we will get a positive answer in quadrant 1. And if we have tan inverse of a negative value, we will get a negative angle in quadrant 4. So when we say it solves for an angle, that means our y values, and we can see them on here, right? Here are your y values that are negative. These are negative angles in quadrant 4. From 0 to -pi over 2 are negative angles in quadrant 4. And these answers are positive answers in quadrant 1 from 0 to pi over 2. So tan inverse solves for an angle. The y values, when you solve for it, you can see from the range, go from -pi over 2 to pi over 2. Converting that to your unit circle, that's negative answers in quadrant 4 and positive answers in quadrant 1. So if I did tan inverse of tan of 2 pi over 3, you're going to be tempted to say they cancel out and get 2 pi over 3. That is not correct. This is in quadrant 2. Is tan positive or negative in quadrant 2? Negative. So if I do tan inverse of a negative, my answer will always be a negative angle in quadrant 4. Still going to be the same family, same reference angle. You're going to get negative pi over 3. Here's our properties. The domain of tan inverse goes forever. Its range goes from negative pi over 2 to pi over 2. In other words, negative quadrant 4 and positive quadrant 1. Tan inverse is an odd function. You can see if you reflect it twice, it matches up to what it began with. This is interesting. You can always cancel out this way. If you do tan of tan inverse of x, doesn't matter what value I put in there, they'll always work out for you, no matter where you put it in. But if you do tan inverse of tan of x, your answers only equal x if you're in that original negative pi over 2 to pi over 2 range. Other than that, you have to use the shortcut that I showed you. That tan inverse of negative values will always give you answers in quadrant 4 that are negative. And tan inverse of positive values will always give you positive answers in quadrant 1. Okay, so now we're going to use our skills at figuring things out. Tan inverse solves for an angle. Did you ever have 1 on your pie plate? For tan. What family is it? Pi over 4. And if we're doing tan inverse and it's positive, we would look in quadrant 1. The answer is just pi over 4. Cos inverse of negative root 3 over 2. Cos inverse of a negative, what quadrant will I be looking in? Quadrant 2. Did you ever have root 3 over 2 as a family? What family is it? Pi over 6. So if we're looking in quadrant 2, it should be 5 pi over 6. So I find those shortcuts are really helpful for just knowing where your answer should be. You're still going to have your reference angles and stuff like that. Sine inverse of a negative. What quadrant will you be looking in? You're looking for a negative angle in quadrant 4. And which family? Pi over 4 family. So which one is it going to be? Negative pi over 4. Tan inverse of a negative. You're going to look for a negative angle in quadrant 4. Do you recognize the 1 over root 3? What's another way you could write 1 over root 3? Root 3 over 3. What family is that?
D is an RD. We have a different D.
You have a different D? Well, I'll do this one then. Yeah, I can do your... There's your D, right?
Yeah.
And your C is different. These are just... You see, that would be negative pi over 6. Now I'll go to your actual C's and D's. Whoops. Sine inverse of sine of pi over 6. This will be positive, right? Because it's in quadrant 1. So I'm just going to put a positive here. Therefore, what is the angle? You don't even have to know the... You don't even have to figure out the ratio. You can, if you know it's a half, brilliant. But if you got it wrong and said it was 2,000 over 5, okay, that's really bad. But you'd still have a positive value. When you undo it, you're going to get the same family. And if it's positive, it has to be that same family in quadrant 1. It's going to be pi over 6. So using that shortcut, no other work needs to be shown. You could, like, If you did this, this is fine. But I'm okay if you go right to the answer just knowing that it's positive. Pi over 3 is in quadrant 1, right? Cos inverse of cos of pi over 3, this is going to be positive. As far as the shortcuts go, did you recognize that all of them, when they're positive, are always quadrant 1? So, what's the pi over 3 in quadrant 1? It is pi over 3. It's the negative ones that are different, and sine and tangent are negative angles in quadrant 4, and cos are positive angles in quadrant 2. That's the part that's different as far as our shortcut goes. Sine of 5 pi over 6, is that going to be positive or negative? Positive. Where are positive angles for sine inverse always going to be? Quadrant 1. So our answer for this is going to be pi over 6. I'm not even going to show you the other bubbles. Why complicate things if we can make it easy? Okay. Now let's get interesting. Remember, if we put arc, that's the same as tan inverse. So we want to find the exact value of cosecant of arctan of 3 over 5. What is this question asking? It's asking for us to find cosecant of an angle. And we know, because arctan solves for an angle, right? It solves for an angle when the tan would have been 3 over 5. That's our ratio. So what can we do with that? Well, I could draw a picture. And since arctan is of a positive number, you know it has to be in quadrant 1. We don't have to draw it in quadrant 3. So this is something that's a little bit more advanced than what you did in grade 11 and grade 12. You know that arctan finds an angle, and that angle would have to be in quadrant 1. And if I draw that picture of my triangle in quadrant 1, if I'm doing arctan of 3/5, I would know that tan of that angle is 3/5, and I could draw 3 over 5. Right, you know your SOHCAHTOA rules? So then here, in this triangle, I am now wanting to find cosecant of theta. And if you've got the triangle drawn, see how easy it is to label that sine of theta is opposite over hypotenuse. And therefore cosecant of theta would be root 34 over 3. So when we get to ones that are involving multiple trig functions, drawing the triangle in the right quadrant is going to be super helpful. So here when I had arctan of 3/5, the 3/5 is positive. I know that my angle theta has to be positive in quadrant 1. So again, that shortcut is coming back to help us. Sine of tan inverse of negative 8 over 3. Which quadrant are we going to be looking in? Quadrant 4. Why? Because tan inverse of a negative is a negative angle in quadrant 4. There's my angle theta. And theta is tan inverse of negative 8 over 3, which means you know that tan of theta is negative 8 over 3. Tan inverse solves for ratios. Tan inverse solves for angles, which means you throw in ratios inside. So using the idea of an inverse, switching your x and y, we know that tan of theta is negative 8 over 3. We label that. And from this triangle, can you tell me what sine of theta is going to be? Negative 8 over root 73. So we use the shortcut to make sure that we draw the triangle in the right spot. And with inverses, our domain gets restricted. Okay, I can keep that there. But shortcut wise, I have sine inverse of a negative. Where will I draw my quadrant? I mean my angle theta? My angle theta will be here, a negative angle in quadrant 4. What can I label on here? I know that sine is opposite over hypotenuse, so I can label this as root 3 and 2. A squared plus b squared equals c squared. You see that will be a 1. So therefore, one of the things by doing this, if we let theta equal sine inverse of root 3 over 2, then this becomes what is cos of theta, right? And you look at your diagram, what's cos of theta? 1 over 2. Is it positive, negative in quadrant 4? It's positive. So we get our answer here is 1 over 2. If you did this the long way, you would have to say, from my unit circle, is the answer ever root 3 over 2 for sine? Oh yeah, that's my pi over 3 family. This is extra thinking you don't need to do. But yes, you could say it's your pi over 3 family, and because it's negative, it would have to be in quadrant 4, so it would be negative pi over 3. Then I have to figure out cos of negative pi over 3. And I'd be like, that's in quadrant 4. Cos of pi over 3 is a half. Cos is still positive. But you can avoid some of that extra thinking by just drawing your picture. And not have to, you sort of skip actually ever figuring out what theta is. Which is really helpful if the ratio is one you don't know. Right? This one, we could say it's pi over 3 family. But we didn't need to know that to solve this question. Sorry. I apologize. I'm adding an alpha minus beta formula. Tan inverse solves for an angle. Cos inverse solves for an angle. And then I want to find sine of whatever this angle is minus this angle. And sine of one angle minus another angle, does that remind you of your sine alpha minus beta formulas? So you would have this alpha and beta minus this. Ugh. But let's make this somewhat easy. Let's look at your alpha. Your alpha is tan inverse of negative 1/3. What quadrant is alpha in? It's negative for tan is quadrant 4. Make that triangle, label the opposite over adjacent, do a squared plus b squared equals c squared, and you get the hypotenuse to be root 10. Beta is cos inverse of 5/13. What quadrant is beta in? Cos is positive. Positive ones are easy. Doesn't matter which one it is. It's going to be quadrant 1. There's our beta angle. Cos is adjacent over hypotenuse. And I could solve for the other side to be 12. So sine of tan inverse of negative 1/3 is just sine of alpha. Look at my alpha triangle. Can you see that sine is negative 1 over root 10? Cos of cos inverse of 5/13 is just cos of beta. Which cos of beta for my triangle is 5/13. That one nicely canceled out because it was in quadrant 1. Cos of alpha, go to your alpha triangle, 3/√10. And sine of beta, 12/13. Which you could simplify. Okay. This is a little bit complicated here. We want to rewrite cos of sine inverse of x as an expression in terms of x. So first of all, what does sine inverse of x do? It finds an angle. And then what is cos of an angle? It'll be adjacent over hypotenuse. But to start off with, we know that solves for an angle. That cos of sine inverse solves for an angle. And that angle will either be in quadrant, this part here is telling you it's either going to be in quadrant 1 from the shortcut or quadrant 4 from the shortcut, depending on whether or not it's positive or negative. And because x can be between -1 and 1, it could be both positive and or negative. Now x is the same as x/1, so if it's positive, it would be in quadrant 1. And if you did a squared plus b squared equals c squared, this side, there we go, would be the square root of 1 minus x squared. If it was in quadrant 4, because it's possible that x could have been negative, which means it could have also been in quadrant 4, then you would also solve a squared plus b squared equals c squared and get the adjacent side to be the square root of 1 minus x squared. So if cos of sine inverse is really cos of theta, and your theta is either in quadrant 1 or in quadrant 4, what is cos of theta? So now I look at my triangles. Could I write what cos of theta is? Yes. In quadrant 1, would it be positive or negative? Obviously positive. What about quadrant 4? Cos in quadrant 4? Also positive. So do you see that this one would be the square root of 1 minus x squared over 1? And this one would be the square root of 1 minus x squared over 1? So cos of theta is just going to be the square root of 1 minus x squared. And it doesn't matter whether it was in quadrant 1 or quadrant 4. And now we've written an expression for cos of theta in terms of x. And this kind of math is going to be helpful for when on Friday we start doing the derivatives of cos inverse, sine inverse, and tan inverse, and cosecant inverse, secant inverse, and cotangent inverse, and learn another 6 shortcuts. How have you been at keeping up with your other shortcuts? Do not ever, ever take a break. Every night, go through, what are we at, 13 shortcuts? Every night go through all 13 shortcuts. Because some of them you will like not use as much, and then I guarantee if you're not going through them, you will forget them. And everything we do from now till the end of the year is dependent on how good you are at shortcuts. Otherwise, you'd have to go back to the definition of the derivative. Not recommended. Okay. The next part is a little bit of review of what we did yesterday. So a little review of inverses before we get to the inverses of the trig using our restricted domain and the stuff that we've been developing. If two functions, g of x and f of x, are inverses, remember the following, that g of f of x is equal to x and also f of g of x would be equal to x. And of course, we learned with trig functions that sometimes things get a little messy with domains. So g of f of x equals x if and only if it falls within the right domain. Otherwise, there's special rules that we saw with certain inverses. Okay. If both functions are differentiable, then we can use the chain rule to differentiate both sides. So if I do the derivative of both sides, the derivative of x is just 1. And the chain rule says, do the derivative of the outside function. See how I have g prime? Keep the inside the same. Multiply by the derivative of the inside function. So there, being able to talk through your chain rule is really important. And if I wanted to, I could get the g prime f of x by itself. And I could rearrange this in either way. And if we took the other one that I wrote in blue and did the same chain rule, we get this formula. And I said, this is a formula that we rarely use. Because if you know on the corresponding point on the inverse, if you know the tangent on the original function is rise over run, the tangent at the corresponding point of an inverse, everything gets switched, x and y, becomes run over rise. And that'll be our main go-to for solving these questions, even though I will show you some work with the formula as well. Maybe I don't want to even show the formula. If I don't like the formula, should I even show it once? No. Let's just do the easy. So f and g are inverse functions. So that allows you to do all the switching back and forth. It says we want to find g prime of 2, and we know f of 1 equals negative 2. And f prime at 1 is equal to 4. So, if you know that you have f of 1 is equal to negative 2, that tells you that you have the point 1 comma negative 2 on f of x, and because they're inverses, that tells you that you have negative 2 comma 1 on g of x. Just switched x and y. If I know f prime at 1 is 4 over 1, at the corresponding point, g prime at negative 2 then would be run over rise 1 over 4. Did we figure out the question? Yes. Not showing the extra formula work, keeping it simple. This is the best way to do this question. Okay. We'll do this one too. F and G are inverses. So what do I know? I know g of negative 1. So I'm going to do f of x, g of x. I know I have this point -1 comma 0 on g of x. So that means maybe my pen ran out of ink. There it is. That on f of x, I'd have 0, -1, correct? They're inverses, so switch x and y. What are we told? We are told that g prime of -1 is -1 over 3. That tells me that the corresponding point f prime of 0 will be -3 over 1. Hey, that's what we want to find. Done. Because your x's and y switch, so if slope is rise over run, it switches to run over rise. Again, that's the simplest way to do these ones. F and g are inverse functions. Find g prime of 4 if f of x is x squared minus 5. So again, I'm not going to show you all of this. I'm going to say f of x and g of x. What did they give us? They gave us only that we want to find g prime of 4 is what I want to find. So that means I have a point on g of x that's 4 comma something, but I don't know what the something is. It also means on f of x, I have something comma 4. This is all the information I'm given. What can I find first? The x of what? How would I find the x of f of x? Right, you're saying I can find this? Well, I've got the equation, right? So if I know the y is 4, 4 equals x squared minus 5, right? I solve for x squared will equal 9, and x would equal plus or minus 3. Is there any restriction that it has to be one or the other? Love how fast this is. Which one does it have to be? Positive 3. Because of something I can't see. Come on. Maybe if I try to write 3. Nope, there's that 3. There's another 3. Somehow it didn't. Will it let me slide up now? Yes. X has to be bigger than or equal to 0. So we know that it's 3. Could you find f prime at 3? Yes, because it's a really easy derivative. The derivative would just be 2x. F prime of 3 is 6. So what is g prime at 4? The reciprocal, 1 over 6. That is the easiest way to solve these. If you want more confusing techniques, come see me at lunch. Like, that sounds like the worst thing ever to offer. I can teach you something much more confusing using the formula and bad notation, but this is the easiest way to solve. Okay, that's where we'll stop.